we're going to be looking at the consistent hash exchange and partitioning a single queue into multiple queues and looking at some of the patterns that we can get from that and avoiding some of the issues that you can get with a single queue, especially when you're trying to scale out with multiple consumers. So the original title had something about it being making RabbitMQ a better broker, but it's kind of more like making it a safer broker. Okay, so we're going to look at a few different things around consistency and safety, among other things. So the kind of easy way to scale out your consumers when you have a velocity of messages that one consumer can't handle. That's either because it takes some time to process each message or it's just because it's very fast. We can just scale out our consumers and have multiple consumers. And it's really easy. You just point your consumer at the queue and RabbitMQ will do its best to distribute those as evenly as possible given the prefetch settings that you've got. And your unit of parallelism here is the consumer itself. Okay? So an alternative way is to use sharding or partitioning. And RabbitMQ has a few options here, and I'm going to be specifically looking at the consistent hash exchange. So in this situation, the unit of parallelism is the queue. So what we do is we actually route messages. We partition the messages based on the hash of a routing key. Okay? And so what we can do is we can actually, rather than using sort of routing keys where we might say, bookings.new, bookings.modified, we can actually put a booking ID or a client ID or whatever as your routing key. And then you can make sure that all your messages related to a given object or entity always go to the same queue and therefore always to the same consumer. And so now we've lost our total ordering of our bookings, for example. We don't have a totally ordered set of bookings, it's now partially ordered, but because of the way we can do routing, we actually get causal ordering, okay? So it's a partial ordering, but we still maintain the ordering that is important to us, which is to say that we're not going to end up processing a booking modified before a booking new, because no doubt you probably have the same application dealing with new and modified bookings, but you don't necessarily want them in different queues because you can then process them out of order. So this is a way of kind of scaling out and maintaining ordering guarantees with causal ordering. So some of the problems that can arise with competing consumers is the weakening of processing ordering guarantees, because anytime you process a single sequence in parallel, the processing of that sequence is not going to match the stored sequence in the queue. We also see that hopefully this is going away soon with the new quorum queues, but with the current HA queues and with the blocking synchronization and things like that, large queues can be quite problematic. And you can get large queues just simply by having some kind of downstream problem with availability of a downstream service. And if you have a high velocity queue, it can grow quite quickly. And then if you have multiple failures, you might be in a situation where you need to repair the replication in your broker, and you can get to some quite difficult decisions. So we're going to look at how we can solve that. Right. So we can get guaranteed processing order of dependent messages with a consistent hashing exchange, ensuring that we use a routing key that does that for us. So with a routing key that's, say, a booking ID or a client ID, we can actually have a single consumer process lots of different events, all related to a client. It could be a new client, it could be a change of address or whatever. You could have all kinds of mashing together of related events, and you can guarantee that the order of those events is going to be processed, scaled out, but also in the correct order. Okay? We also get data locality patterns because we now, all of, say I'm on my company's website, which is Vueling, the airline, so I'm making some bookings. All my bookings are going to be consumed by the same consumer. And so we can get some data locality patterns where we can do some in-memory stuff. So we don't necessarily always need to be using a cache because we've got stuff in memory that we can keep around. And we can also reduce queue sizes, which is related to what I was saying about HA and Rabbit. So let's have a look a bit more. So here I've got a kind of a safety scale from green is pretty safe to kind of orangey red to not necessarily safe, okay, regarding message ordering. So regarding message ordering, the best you can have is that your messages are independent, right? So this could be your logs. If you're using RabbitMQ for your logs, it's essentially just each log event is independent. When you need to order them, you'd be using your data store to do the ordering. The fact that you are processing them in different order doesn't matter because you're just adding it. It's like an append-only operation. So when messages are independent, you don't really worry about message ordering at all. Then we've got the one consumer per partitioned queue. Okay, so this is what I was saying about using the consistent hashing exchange, also known as consumer groups for people who know Kafka. Okay, and as long as each consumer is processing its queue and sequentially, then we still maintain those ordering guarantees. Now, less safe, but can still be safe depending on how close your related independent messages come in the queue. When you have a prefetch of 1 and you have a constant processing time or a short processing time in your consumers, then more or less you'll be getting very close to the order you get in the queue. Now, it won't be perfect, but if you've got related messages coming in minutes apart, then with a prefetch of 1, or even if you've got seconds apart, then most likely you're going to be fine. Where things start getting a little less safe is when you have a large prefetch. So if you have a prefetch of 10 or 100, now you're talking about RabbitMQ delivering messages in kind of batches. And so now your total ordering is getting more and more out of whack. The larger the prefetch and the larger number of consumers, the further out of whack your ordering is going to get. And also, the more variable your processing times, also, with competing consumers, the more out of whack your processing is going to get. And the worst is when you have long and variable processing times with a large prefetch. Now, take all this with a grain of salt, because if you do have 5 or 10 minutes between each message, it's probably not going to matter. But if you are in situations where you can have state changes to objects that can be very close together, or if you're in a situation where you've had some downtime and your queue is full and now you're catching up, you can actually have messages actually temporally are separated by a few minutes, which are actually very close together in your queue. So we're going to do a couple of demos, okay, just to kind of see this messaging ordering. We're going to have a first demo. I've got basically a publisher, and all it's doing is it's got a key, A, and it's going to publish a series of state changes to that key, basically a sequence of monotonically increasing integers. And it's going to publish that, and we've got 4 consumers that are going to process that sequence in parallel and publish that out to this consumer, and the consumer is just going to print out what it gets back. And we'll see that with competing consumers, even with basically 0 milliseconds of time, it will be out of order. Then we'll do, when we've got multiple keys, this would be more like what you'd have in real life, would actually have, each of these letters could really be a booking ID or a client ID or whatever. And so we'll be publishing multiple keys, and we'll see what the kind of causal ordering effect is on competing consumers, and we'll be comparing to see if the order is correct for each given key, okay? And finally, we'll be doing exactly the same, but we'll be using a hashing exchange and just seeing how that affects message ordering, okay? So we're going to jump out of here. I'm going to jump over to my Linux box, see if I can get my password right. And no. Okay. Right. So in this box here, I have the publisher, okay, and this is going to be basically publishing a set of one key, which is just key A. It's going to send 20 messages, okay. Here on the right, I've got my my consumer that's just simply going to print out the sequence that it gets back. I'm going to start at my consumers, okay? Each consumer has got a prefetch of 1, so it's on the safer side, okay? We've got 0 milliseconds, because I can configure here some extra milliseconds of processing time, okay? So I've got, do you know what I'm going to do? Because it's more interesting. I'm actually going to do a first run with just one consumer, okay? And we'll just see what happens when I publish 20 keys. Let's just skip my... So we see on the right there that our sequence is perfect, okay? Because we've got one consumer. So we just start up my other 3 consumers here, okay? And we'll do the same again. And now we see that we've got all kinds of jumping forwards and backwards. We've gone to 1, 4, 2, 3, 5, 7, okay? And this is normal, and you will always get this. But this is just of a given key. It's unlikely that you're going to be making hundreds or thousands of changes to a single booking within a period of milliseconds. So let's make a little change to our consumers and just see what happens when we do something else. So we could, for example, increase the, let's add a little bit of variance in our processing times. It's not much. Okay. Okay, and we get them all right. Okay, so there's a little bit of variance, and we'll just see what happens. More or less, it'll probably be something very similar. Oh, and I'm going to start sending 5 keys now. Okay, so we're going to have keys A to E, and we're just going to see what happens to the order. So we actually see that now we've got multiple keys. The fact that the total ordering is still wrong. I mean, if you look at the letters, you can see A, B, B, E, D, D, C. I mean, the total ordering is wrong, but because we've got some space between events, the actual causal ordering between the different state changes is fine, for the most part. We've got a little bit of jumping forwards and backwards, okay? But the final values are still correct, okay? So with prefetcher 1, things aren't looking too bad, actually. So what we can do now is we can actually slow down one consumer, okay? So we're actually going to make one run a bit slow. Now, this does happen in production. You can get one consumer running significantly slower than the others, okay? Could be due to CPUs being maxed out, just some weird anomaly that no one can explain. But when you've got one slow consumer and you've got competing consumers, now you're going to start seeing greater disordering. Okay? And so we actually see now the final value of C was wrong. Okay, and we can run that a few times. But we're still limited because the prefetch is a very safety-oriented setting. It's not great for throughput, but for safety and distribution, it's your friend. So here we get A is wrong here. Okay. Now, if we combine the fact that we've got one slow consumer and we've got a higher prefetch, let's just say of 10. This is when the ordering starts getting a bit worse again. So let's just run it again. Look at that. Yeah, that's pretty bad. Jump it backwards and forwards quite a lot, and we get pretty bad values now coming out at the end. Because we're very sensitive to one consumer that's running pretty slow and is also getting in large batches of messages at a time, okay? But the problem is that quite often you might want to hire prefetch because you do have with prefetcher 1, you're basically, your consumer's saying, hey, give me a message. You get a message, you hack it, give me another message, and there's a lot of back and forth, a lot of traffic, and it reduces your throughput significantly, okay? It has a large impact on throughput. And so if you really want to have high throughput, but you want to have messaging ordering safety, and you can be in a situation where you're quite sensitive to message ordering, then that's when the partitioning can help. So let's just have a quick look. Let's just shut down my consumers. So here I have a few, I'm going to just run it with the worst case. Okay, so we got prefetcher 10. I'm going to run one that's a lot slower, okay? So again, 100 to 2 millisecond processing time, whereas the others are sort of 10 to 30. Okay, and we'll just see what happens now. So I'm going to run it from the bottom window. Okay, so we can send 20 messages per key, 5 keys, and we'll see that message ordering is perfect. And you can see that all the B keys came in last. Sorry, not B, that's the binary, sorry. The D came in last because that was the slow. All the D keys were being routed to the slow consumer. Okay. So if you do have situations where you need to scale out and you do want higher throughput because you want to use a higher prefetch and you're worried that you can get messages being processed out of order and that can introduce sort of errors and undefined behavior in your system, then it's something to consider. Right, let's just jump back into the presentation. Okay. Okay, so other things that you can do. So one of the data locality patterns is actually deduplication. So when you have a producer that is produces a series of messages and you get a connection failure or whatever, or node fails, you don't know if those messages have been persisted safely, so you might choose to resend, at which point some were persisted safely and now you've got duplicates. Okay, so on the consumer side, you can try and go for idempotent processing. It's not always possible though, if you're sending emails or whatever, so some things aren't idempotent and you want to deduplicate instead. So you might go for a strategy where you're storing correlation or message IDs in Redis or Postgres or something, whatever, and you're just doing lookups, okay? This can be inefficient and slow, and also is no guarantee because two duplicates could come back at the same time, and you could have two different consumers do the same check against Redis, and Redis will say, no, I haven't seen that message ID, and so the duplicate gets through. Whereas when you're having all your dependent messages all routed to the same consumer, now you can actually make some bets that you can't with competing consumers. One is that you can actually store stuff in memory. So we could actually, the most sort of simple way of doing it, not necessarily the best, is to store your correlation IDs or message IDs in an in-memory map. A linked hash map is nice because you can actually expire your messages because you probably don't want to store every message for all time because you might run out of memory. But there's other combinations of queues and maps that you can use. You might have an embedded database, or you might use a Bloom filter, which is great for having duplicate detection in a small amount of memory. But the complication is that your consumer might need to be shut down or it might fail. And now your in-memory data is gone. So you might want to look at snapshotting your data periodically, and so that a consumer that comes to replace your lost consumer can then recover the data. Now, obviously, it's periodic, which means you wouldn't get all of the data. So it's no silver bullet. So some other things you can do when you always know that your a given booking ID always goes to the same consumer is we might have some business rules. So we might say, a client can't do more than X actions of type Y within a period Z. Well, we can store all that in memory. Just, client ID, X actions within a period, and you can just be doing in-memory lookups, and you don't need to be making queries against the database to say, hey, can this guy do this? I'm going to do a SQL query and with my where and whatnot, and have to wait. And your DBA is angry because you're doing the same query over and over and over again. Well, now it's in memory, and you can do that in memory. So I did another little demo where we just implement deduplication, and it's just I'm using Python, just in Python client. I'm just using a dictionary, and I'm simply just doing a lookup. And so if I've seen it before, they just ignore it. So we can just jump back over. So this time I can configure them to say, hey, check it, look for duplicates. If my keyboard will work. One problem is I'm English, but I live in Spain, and so I have a Spanish keyboard, but I have the English setup. So Just trying to remember where all the keys are. Because the Spanish way is just crazy, it's not as good. Okay, almost there. So they're all running. So all they're doing is they're just using in-memory dictionary. I'm going to send some messages now. And I'm going to put a 50% duplication rate. So this is going to simulate producer-side or publisher-side duplications. 50% is quite high. But as we publish it, we'll see we get no duplications at all. And I could run the computer consumer one, but there's probably no point. But it's just a thing you can do because you can make certain bets now that data always goes to the same consumers. Okay. Right, so this is something which I was very happy to learn today, that we are having the quorum queues, because this is something that's bothered me about RabbitMQ and many others. Okay, but queue mirroring, when you have a situation where you need to synchronize an empty mirror, it is blocking, which makes your queue unavailable, which is why they always recommend don't have large queues. So with mirror queues, you have a master and a mirror, okay, and publishers and consumers both read and write from the master, and then all the messages and all the acknowledgements and everything are replicated to the mirror. When we lose a mirror, and we've said that we want exactly 2 replicas, then RabbitMQ will say, great, I'll create another mirror on node 1, but it's empty. Now at this point, let's just say we have 1 million or 10 million. If we have a large queue, this is problematic. As the administrator, you now got the choice. Do I risk having no redundancy now, given that I've already lost a node, or do I synchronize? And if I synchronize, my queue is going to be unavailable. And how long it's going to be unavailable depends on the load, the network, and how much data there is. And so you might just hope for the best and just choose not to and wait for just the natural synchronization as messages are consumed and added for the natural synchronization to take place. But if you do have large queues, or you have a situation where you have a high velocity queue and you've had a history where maybe downstream services are unavailable and you have periods where your consumers are slow or they just can't run and your queues can quickly grow, then one strategy, okay, is to partition your queues. Okay, there's more than, it's not just the consistent hashing exchange that does this, but and now we can actually say, well, actually, I've got 10 queues, which means I've got 10 masters, and it means that if I lose, and this is a larger cluster as well, because if I'm worried about this, then what I can do is I can actually distribute the same amount of data, but over more servers and over more queues. Now, why over more queues? Because each queue is linked to a core, okay? And so one of the bottlenecks in synchronization is CPU, and so, if you've got 3 or 5 or 10 gigs of data to synchronize and it's on one core, then that can be your bottleneck. But we can now leverage multiple cores on multiple servers so that when we do lose a node, and we've promoted a couple of mirrors to masters, and we've created another couple of mirrors that are empty, we can now synchronize much faster because we've got smaller queues and each one is a separate core, and so we can get much better parallelization of our synchronization. But you can forget all that when it comes to mirror to the quorum queues, which will not throw away all their data. Okay, and right, so things that are hard about the consistent hash exchange. I just received news yesterday that one of the things that are hard will be hard no longer. There has been work done on consumer group functionality, so that means that one of the hard things has been consumer group assignment. So if you've worked with other message brokers that have partitioning, they give you out of the box queue consumer assignment. So you just basically set up your queue. You say, I'm in this group, and I want this topic, and it will just assign automatically your queues. But RabbitMQ, right now, we don't have that. So I created a little project called Rebalancer, which is just temporary because I've heard now that Pivotal are actually implementing consumer group functionality in the Java client. So I don't know any details more than that or when it might come, but it's definitely a welcome thing because you can, if you've partitioned your queue into like 20, you can use your configuration and build system, but it's not ideal. So what Rebalancer does is it just does it dynamically using a simple consensus algorithm. And then the other hard thing about data locality is state. Okay, so great, now we can do things very fast in memory, but now it's in memory. And so anytime you need to shut down a consumer or you lose a consumer, you need to think about getting that state back. Okay, so that actually might be more complicated than the problem you're trying to solve, or it might not. That's your decision to work out. And also changing the number of queues also changes the hash space which each queue is related to. Okay, the way I understand it is they try to limit that change, but if you've gone from 5 to 20, my booking 1 that was going to Q2 might now go to Q5, okay, because all the hash space is different, okay, differently distributed. So that's something else to take into account. So I was going to do a quick demo of Rebalancer, and this can act as a little bit of a primer, I guess, on consumer groups that hopefully will be coming with the Java client and other clients. But basically what Rebalancer does is it's a library which kind of sits on top of the current kind of client, and you just say, hey, I'm in this group, and it provides hooks, some events for when you get assigned a queue and when you get disassigned a queue, and just allows you to start your consumers up and shut them down on those events. And so it uses a backend store, can use like a distributed census store or any database that has serializable transaction support. And so what it will do is it will create this number of consumers. It will always have one consumer per queue, and it will just create multiple consumers in a single application. So if I've got time, yes, I think I do. I'll just do a quick demo of that. So this is a .NET application. I'm just going to run it in Windows. Okay. So I've got here I've partitioned my input sequence queue into 15. Okay, and this is exactly the same as my other demo. It's basically got a publisher publishing monotonically increasing state changes. My consumers then process that by simply sending it out again to the single output sequence queue. And we see the final kind of ordering that we get. Now, we've got no consumers right now because nothing's running. But what I can do is I can start a single consumer. And I've said it's in the particular group. And it's a little bit, I'm not sure if people can see it when I make it small. But it's decided now, because it's the only consumer, it's taking all 15. Okay? So I can start another couple of consumers. And it will suddenly realize, hey, there's other consumers, and now they're sharing them out again. And this is basically how consumer groups works. Okay? So they will communicate between themselves and an external store to agree on who's got what. And now if we go to we see that all the queues have a single consumer. So that's all I had to do. I just had to start a consumer, tell it the group, and it started consuming. Okay? So I can send some messages. So 5 keys, 20 messages per key, and there we go. So everything's in the right order. Okay? So per key, I should say, is everything's in the right order. So, you see C20, 19, 18. Okay? And we can go around starting more consumers and killing consumers, and they'll automatically rebalance, hence the name Rebalancer of the project. Now this is could be more of a primer for what's coming with the consumer group functionality in the Java client. So if I just jump back, so yeah, they're just rebalancing now between them. So queues 1 to 5, 6 to 10, 11 to 15. And at no point will you ever see 2 on the same queue. Because if you want to maintain your message ordering, you really need to make sure you have a single consumer per queue. So that is that. So it's question time.
Hey, You mentioned during your presentation, for example, sharding by, for example, account ID. Imagine like we were processing tweets, and one of the accounts is like, for example, a celebrity and has like a huge load, and the consumer cannot keep up with that load.
Right. Yeah. So I mean, there's all kinds of things. So you can actually, if you want to avoid some kind of hot, keys, you can actually almost kind of add some randomness to the key. So you can add like a couple of bits of randomness, and just so it will get distributed. So you lose kind of your total ordering of that given key, but it means you kind of, I think they call. I saw an article a few years ago call it fuzzing keys. So you can fuzz them a little bit, just to add a little bit of randomness, so that you can distribute it a bit. So that's one thing you can do. Okay.
A leading question. Do you think too few people know about the consistent hash exchange?
Probably. I don't know. I don't find many people using it. It's not something I see used. It does ship with RabbitMQ, but you have to enable it. I mean, maybe that's why that you have to enable it. It does come with RabbitMQ. You just have to enable it as a plugin. So.
No, I agree. I think it should be much more utilized.
Hi, thank you for your talk. I have two questions, actually. First, do you see any consistent hash and exchange, the plugin improvements that would make what you demonstrated easier?
Deployed where, sorry?
Can you think of any consistent hash and plugin exchange improvements that would make what you demonstrated easier?
Easier. Well, consumer group functionality on the client, okay? So that you can just, from your client, just say, hey, I'm in this group and I want to consume this kind of set of queues. Just have maybe an abstraction like a topic or something, and then it does it all for you, That's what I think would be easier. I mean, I don't have the code here now, but with Rebalancer, you just say, this is the group, and you kind of have an abstraction of like a topic. One other thing which might be interesting is, and I don't know how difficult this would be, but one of the impacts you have when you start having multiple queues is that the multiple flag usage on the publish confirms starts getting less used, because the broker is having to get responses from so many different queues that you end up getting a lot more chatter, and you can actually slow down your producers in certain cases. Because whereas before you might be publishing to a single queue, and you might publish 1,000 messages, you might only get 4 or 5 confirms back from the broker because it uses the multiple flag. Whereas when you have, say, 20 queues, you might end up getting 800 confirms back. So that's something else that is one of the downsides. But that applies to any situation where you have multiple queues receiving a message. So anytime you're using the topic exchange and you have multiple queues receive a message, you're going to be seeing a less efficient usage of the confirms.
That's publisher confirms, right?
Yeah, publisher confirms.
Yeah, and my other thing is not actually a question, but in 3.7.8, we significantly improve hashing characteristics of this exchange. So if you previously ran into, not exactly balanced things, and you're sure that your routing keys are well distributed, take another look, because it should, we have statistical tests that demonstrate that it's basically almost perfect. It uses a paper published by Google, Jump Consistent Hashing. So yeah, there are some notes about that in the README now. Thank you.
Thank you.
Okay, any more questions? No? All right. Thank you very much, Jack.
Okay, thank you.